presume you're in the room to hear this talk. If you are not, now's a good time to leave. Hopefully, we'll have some fun. Hopefully, it'll be interesting, entertaining, and informative. So let's see where we go. I'm Pete. Hi. I'm a programmer. I'm an author. I'm a columnist. I'm also really, I've not really spoken in a place that's like people are sat behind desks and I'm constrained behind a table. I kind of want to walk around a bit. So apologies if I start to get a bit pent up and frustrated. But I'm a teacher, author, columnist. I like to call myself a conscientious coder, making the world better one line of code at a time. Just so that you kind of have an idea about me, I've written a few books on software programming, becoming a better programmer. Which of you guys were here last year at the Dew Summit? A few of you. Cool. Okay, so you heard me speak then. I gave a talk called Becoming a Better Programmer. I write magazine columns. I've been doing that for about 16 years. It's called Becoming a Better Programmer. So this is something I kind of really care about. I've contributed to lots of other books. And important thing to point out, and I pointed this out last year as well, I do not want to pretend to be any kind of expert or genius. No, don't necessarily believe everything I say. It's going to be good stuff, but just take it with a pinch of salt. Keep your thinker switched on. I'm still learning as much as anyone else is in the industry. Also, I head up software in music, so that's Akai, Newmark, Oasis, M-Audio, lots of brands, and we make really cool, fun stuff. And I love my job. It's cool. We make fun stuff. So check out our things. This talk is apparently an hour long. Originally, I was told it's 45 minutes, so let's see how long it takes. It'll be interesting. It's an adventure for me as much as for you guys. Also, fair disclaimer, unlike most of the other talks at this conference, this talk was not peer-reviewed. I was invited to talk. So what you hear may be theologically incorrect and utter tripe, in which case blame me and don't blame anyone from the conference. I think that's just a fair disclaimer. Of course, it will all be marvellous. The plan is this, and hopefully I will stick to it. I waffle for a bit. And you nod, and this is where you begin to fall asleep. Then I'm going to make some assumptions about what our shared language is, so that we're talking about the same thing. I describe the landscape of audio programming, and then these mythical rules that you're here to find out about. And at the end, you applaud, throw roses, your underwear. They'll be marvellous. So, the rules of audio programming. In the synopsis, I said this, that there are these common bits of wisdom that audio programmers pass down, father to son, generation to generation. These are the things you must never break. They're the fundamental tenets of what we do, and we have to pay attention to them. And I mean, I guess a number of you guys are experienced audio devs, and you probably know all this stuff, which is cool. Nod and agree. I'm guessing that some of you are super awesome, and you've got it covered. Some of you, it's probably a good reminder for this kind of stuff. And some of you guys are maybe newbie audio devs, and hopefully this will be super useful for you. So yeah, these rules are passed down, as I say, from father to son, mother to daughter. We talk about them around the fireside. Campfire songs are written about these rules of audio development, and we must not ever break them. Apart from, let's work out how we can break them. Rules, schmools. So all of these rules come about from experience, from things that we have seen work and not work, and they give us a framework within which we solve the problems that we have to solve. As I say, we can break them. You can prove anything by finding someone who has a quote that agrees with you. So throughout this talk, you'll find lots of quotes that agree with me from very wise, intelligent people. So it's wise not to violate rules until you know how to observe them. T.S. Eliot, clearly, again, I'm talking marvellous stuff. Picasso, learn the rules like a pro so you can break them like an artist. And I mean, I hope you guys think, we're writing audio code, we're making fun things that people interact with in an interesting, visceral way. What we program, it's not science, it is an art. We're making beautiful things. So I think this is kind of like really important. And why, some of the rules are kind of dull, they're housekeeping, they're mundane, but it enables us to make these beautiful things, and that's what I really care about, this kind of stuff. So, the assumptions that I make, if any of these don't hold, you are free to leave, except I'll shoot you later. Oh yeah, what a man believes may be ascertained from his creed, not by the assumptions with which he habitually acts. So these are the things that I think constitute what most of us here think of as audio programming. So audio programming here, we're we're really caring about the real-time performance of our application. Now, this might be like we might be writing something grand like a DAW, something, a synthesizer, either a standalone kind of thing or a VST, DJ product, an insert effect, that kind of stuff. The key point there is we are talking about real-time audio applications. If you're doing something like iTunes, a media player, the constraints are very different. You don't have to process stuff in real time. You can be buffering up an awful lot of audio or just doing some simple pipelining stuff. We care about real-time audio performance. So that's one of the assumptions I'm making here. And I think it's a fair guess. You know, we're talking in a C++ kind of environment. If you're writing your audio application in Eiffel, good luck to you. And this could be desktop software, it could be an embedded product. Most of this stuff applies equally in both of those kind of environments. So those are my assumptions. Now you walk out. The landscape of audio programming then. So it's important to consider this up front because we might be making decisions or optimizations or something in one context, but let's just stand as far up as we can and look at the thing that we're building to inform how we could build it better. Not making micro optimizations, but looking at the system from its largest, from the highest level. There are two main things that our real-time audio code is going to sit within. The CPU, the execution environment, the CPU, the memory, the actual processor, the computer, whether it's embedded or desktop that you're working in, and the buffer sizes, because all real-time audio application is just making audio whenever audio is needed as fast as you can possibly make it. This will become a running theme. So, CPU speeds. This is quite an old graph. It was the latest one I could find from my, until I got bored Google searching. But this is a graph of processor speed versus year. And I mean, I guess we have seen this. I would like to have had a more up-to-date one because the key point to take away here is, as I hope we all know, the trend is flatlining in CPU speed, yeah? So Herb Sutter's The Free Lunch is over. We know that, so Moore's Law is famously not, so Moore's Law being the number of transistors you can pack onto a die doubles every 2, 3, pick a number, break your ass. It consistently grows with time. The number of the number of transistors on those dies has still been growing, but CPU speeds are tailing off because why? The speed of light. No, because of multi-core. Instead, we still have transistors. We're still packing more transistors onto dies, but we're having multiple cores on the same die. So our CPU graph is trailing off, but we're having CPUs with multiple cores in them, yeah? So that is one of the parts of the landscape. Does multi-core mean you can do more? Probably. So most when did someone last make a desktop computer with only a single core CPU in it? Such a long time ago. We kind of don't care. So you can almost take that for granted on desktop computers. In the embedded space, when did someone last ship a phone or a tablet now? We were just in Dan's talk, we're thinking, is a mobile phone as an iOS device, is an Android thing embedded? He says no. Good, okay, so it's not, so that's a computer, fine. But there's lots of embedded things that have these same kind of ARM chips in them. When did someone last ship anything like that with a single core ARM chip in it? There are some. Even the microcontrollers now are increasingly multi-core. XMOS, sort of ARM-based chips, for example, multi-core microcontrollers. So multi-core is everywhere. This does mean we can do more as long as you do the right things. If you write your code really well, you can do less with more cores. So let's just bear that in mind. If you have multiple cores, clearly all you have to do is just spawn threads left, right, and center, and everything will go really well. I still threaten to cut off the hands of anyone in my team who writes the word thread in their code. It's a dangerous, pernicious thing, and we have to wield threads with respect and care. So this is the point. You have multi-cores. It doesn't mean you can just write what you like and you gain more performance. Audio programming is, by its very nature, multi-threaded programming anyway. So multiple cores allow us to do stuff that the structure of our projects want to do anyway, as in keep the UI separate from the audio thread. So this is, it's beautiful happenstance that multi-core has occurred at the same time, well, it has occurred now, and so we can sort of exploit this in most of our designs, but it doesn't mean we can be sloppy. It doesn't mean we can just presume that that gives us kittens, fairies, and performance without thinking about it. So also, just because we have multiple cores doesn't mean we could just, and a faster process doesn't mean we can just relax, not optimize, not care about the quality, the speed of our code. Because if you're writing a software plugin, you probably want to have multiple instances of your plugin running at once inside one DAW. So even if you can run one instance on your CPU, cool, relax, no need to optimize. Can you run 5? And I guarantee you, if your software synth is great, you will want to add more features. You want to add deeper modulation matrices, support more voices running at once. So you'll always want to add more features. This is a classic as well. You write your code for a particular platform, and that's great. So I'm going to write, I presume the user has at least an i5 running at 2.4 gig. We'll see some numbers about those in a minute. So that's cool. So that's my minimum spec. And then somewhere down the line, you decide to port it to a mobile platform. And all those presumptions you made about that wonderful processor fall on the floor as processor speed and the memory bandwidth environments fall around you, and you have to completely write from scratch. So there we go. These are the times we live in. So CPU speed, and it's not just CPU speed. I won't go to town on that, but also the memory bandwidth is an important thing. Different platforms have different access speeds, different bus speeds. You've got different processors have different cache topologies, and that, again, really changes how your code would perform, and you have to be thinking about those kind of things. That's very much, I think, what would characterize the embedded side of this thing, where you take more of a systems approach. You're really thinking about the execution environment more than on a desktop audio application, perhaps. The other thing, and this is where now we're beginning to get into the tedious stuff, where audio buffer size really affects responsivity, and what we need to do is make highly responsive, real-time, performance-based things. So if this is time, the relentless march of time going on down here, and every now and again we need to produce an audio packet of this size. You set a buffer size, don't know how many, maybe it's 256 samples, whatever. At some point, the user presses the honk button, expecting immediately to hear a honk. But they have to wait up to 256 samples before. So we already have this buffer in flight, and they have to wait, and they have to wait, and they have to wait. And a little while later, 256 samples later, which is an age in CPU terms, honk. Now, this is not a performant real-time audio application. So what do we do? What do? We want to aim to reduce the buffer size, so when they hit the honk button, it'll be a very short time before they get a honk. And if you do it really well, the honk is smaller than a packet size, so you'll probably have a honk, and then a bit later on. That's what we're aiming for. So that's simple, isn't it? Smaller buffers is more responsive. And that is hard because audio, if you're trying to optimize our code, if you're trying to run smaller buffer sizes, the CPU has less chance. You're not exploiting efficiencies from caches, optimization of algorithms and loop unrolling, all that kind of good stuff. So you'll have a harder hit on the CPU, even though you're effectively doing the same amount of work with those smaller packets. So we need to aim to get our code performant and work well with these smaller buffer sizes. Somebody said to me, when I described this as somebody once, they said, oh, that's simple. If you want to solve this problem, you just process the input more often in the packet size. Simple, isn't it? Duh. No, just to say, this is one you can't, this is a rule you can't break, this is something you can't cheat. If you process your input 4 times within that one buffer size, that's fine, but you're still building the audio ahead. So even if the user presses the honk button here and you process the input here, there's still a delay in how the input comes out. So you may win a little bit of responsivity. This is not the way to solve this problem. You have a sort of hit, honk, rather than a hit, honk. But these are the things we work with. So the rule, and we know this rule, don't we? Audio buffer generation must take longer than the period size of the buffer playing back. 101 audio programming. Why do we get this so wrong? And we know what happens. A number of people have been talking about this in this conference already, but if your render thread sort of just is wandering along and then suddenly decides it's a bit tired, takes a nap, sits down, wakes up a bit later, feels refreshed, but then takes longer than its period size, then you've got to drop out because audio hasn't made it to the to the sound. So you click on a pop, and then the next packet's like, oh, I'm a bit delayed. Come on, hurry up, get out of my way, and then the last packet's falling off the back of the bus, and the user's disappointed, and your audio sounds terrible. And this is the important thing. Any audio program, this problem is not specific to audio programming. All threaded programs have this kind of issue, and the VR guys sort of have these kind of hard real-time constraints as well. But for us, in the kind of products we're talking about, you hear a glitch it's more obvious than a visual glitch in the kind of applications we're producing. Specifically, this is like, I went back to some of the oldest research I could about this. So this is a 1968 study. I believe this was one of the first ones about looking at UI response in computing systems. And the study there showed that a response time of 100 milliseconds was perceived as instantaneous. Now, again, this is in 1968. These days, you know, with more caffeine and ADHD, we may expect, you know, our expectation of computing systems is higher. But again, the perceived 100 milliseconds is perceived as instantaneous. For them, a second or less of delay is like, nah, it's all right. 10 seconds, then you've lost their attention. So, you know, maybe the numbers change, but that's the kind of ballpark we're playing in, certainly as what is perceived as instantaneous in static UIs, sort of virtual reality immersion. It's a different thing. But the audio response, again, this is the earliest research I could find on it. If you know something earlier, please tell me. 1949, they were measuring the perception difference of gaps between audio. So things between 1 and 5 milliseconds, those sounds were considered instantaneous. Now that's important because say if you're making a drum machine, you hitting the pad and the sound coming out within those 5 milliseconds, that will be the instantaneous. That's like the real-time response we're aiming for. Anything up to 40 milliseconds for more complex sound playing back was sort of felt instantaneous, but again, that's more your iTunes kind of style stuff. So we're definitely, we need to aim for this 1 to 5 millisecond kind of performance thing. And anything longer feels like an echo, as in it's not what we're aiming for. So like the numbers say that we have more constraints on the audio throughput than the visual side of stuff. We can't miss our buffer periods, and anyway, if we miss our buffer periods even once, we get that click, and we really don't want that click. So we know this stuff, hopefully. I'm just reminding us, nod sagely, hooray. So based on those facts, the rules of audio programming, the golden rule is there are no golden rules. The first rule of Rule Club. So rule number 1, I'm just going to say what I just said again in a slightly different voice. You must keep within your CPU budget. Yeah, and even Shakespeare agrees. Shakespeare, the original awesome audio programmer. So, yeah, that diagram I just showed you, you can't have your audio buffer, your audio render process fall asleep and fail to get audio out in the time slice it's allotted. It's just unacceptable. So we have hard constraints to work within. Now, those constraints aren't necessarily that constrained. Let's say we're working down, we're doing something beautifully real-time, DJ application, software synth. If we were going at 44.1, a 64 sample buffer size, which is very achievable these days, that is, you have to generate only 1.45 milliseconds of audio, but that's a beautiful response time. Even if you come up to 128 samples, that's 2.8, so 256, these are achievable numbers. What that means on and this is like a very pedestrian 2.4 gig i5, say, you have a metric shenanigan of instructions. So actually, the CPUs that we're working on, at least on desktop systems, there's no way we can't make beautiful audio with that many millions of instructions. Cool. So why do we get it so wrong? And don't forget, on a modern desktop platform, you have 4 cores doing this as well. Jeepers, we are spoiled. Oh, I remember when I was a lad, we had 16 instructions to rub together, and we had to and we had to keep ourselves warm whilst we did it. So those good old days. Let's say this is the UI work that we do, and this is the audio work that we do. We have to keep processing our audio reliably. Multi-core gives us the ability to not have contention on the one core. That's great. We're all happy. And so this multi-processing model is great. As long as, and we know this, as long as our processes don't depend on each other, and we write our code very carefully so that the UI work does not block, stall, or interact with in bad ways with the audio thread. Most of this talk will be highlighting ways with which we do this wrong. But again, thinking about this, because it's a fair ask to say, what is your deployment target? The thing about a multi-core i5 means that we can rely on multiple cores and doing this kind of stuff. Cool. So if you say your minimum sort of spec for the code you're writing is this world, you can do as little or as much optimization to hit that platform target as you want. That's cool. Except so many projects I know then move platforms. So it's a question that's always in the back of your mind. What is your assumption about the platform you're running on? Because I bet you in 10 years' time, it'll be wrong. Sucks to be you. So that rule, number one, what I'm trying to do is highlight the rules, the golden rules of audio programming, and then work out how we can break them. This one, you can't break. You can't not render your audio in the CPU budget you have, even though the CPU budget is huge. So there's no problem, is there? So you can't break this rule, except, well, yeah, okay, rules are there to be broken. We can, and Marilyn Monroe, if I'd observed all the rules, I'd never gotten anywhere. So let's just, how can we flout that rule? And, well, it's not really flouting, it's not really breaking, it's just designing well. All the stuff that you might do on your audio thread that would cause it to overrun, just don't do it on your audio thread. Simple, isn't it? So all that slow calculation of coefficients, push that off somewhere else. Maybe in the design, if you're running multiple, if you have like sort of multi-channel audio playback, if you have a sequence of running within your thing, then push off the rendering of the things that aren't actually needing to be real time. Maybe one of your tracks is sort of the user can drive in real time. The other ones, if they're not in real time, punt all the generation of that audio off so that it's not going to clog up your audio thread. All those kind of clever things. We heard some talks yesterday on audio visualization and audio analysis. Don't do that on the audio thread. Duh! And more intelligently, if you have processing that is quite intensive, if you can split these things, if you can amortize it over each of your audio render blocks in an intelligent and cunning way, then you can sort of gain lots of wins. We'll see examples of some of these as we go on through the talk, but the point is, even then, it's not breaking the rules per se, so that's not necessarily fair. But you know, we can do stuff to arrange not to overload our CPU budget by just smearing our work around the system. Rule number two, which is basically a corollary, I guess, of rule number one, but this is where it gets important. And most of the talk, I guess, is basically around these rules, this particular rule. And what I'm going to do is increasingly take away all of your shiny toys. If you don't know how long the work will take, do not do it on the audio thread. That is basically the golden, shiniest golden rule of all. And this is about the relentless march of time. Every talk has to have a Dr. Seuss quote in it. It's the law. They say I'm old-fashioned and we live in the past, but sometimes I think progress is too fast. Deal with it. This really is about those two beautiful things, latency and jitter. So latency is what we've just been talking about the reactivity of your app. But this rule is all about jitter. It's fine if you have a 3 millisecond audio period, that's cool. And if on average, your code only takes 2 milliseconds to render that audio, so you've got a whole millisecond to spare and sit down and smoke a cigarette and have limoncello on the veranda, and then come back the next millisecond to do some more audio. That's wonderful. Except if every now and again, it's so rarely, every now and again, your audio render takes 4 milliseconds, that's not acceptable. It has to always take less than 3 milliseconds. That jitter, even if very occasional, is the killer. And this is the key thing, because from the sort of the numbers I showed you, from the studies I showed you before, we hear clicks. One click, the user hears that. It could, I can't remember who said this earlier, it could literally kill a DJ set. If there was one click in a DJ performance, then game over. It's terrible. But trying to track that down with an instrumented build, running profiling, whatever, you can't find the thing that caused the stall. So we have to be Neanderthal on this. Jitter is unacceptable. Oh, talk underrun. So, I should have buffered up more words in advance. So, how do we, what things affect, what things don't run in bounded time, and how do we avoid doing them? How do we break the rule, or how do we keep that? So consider algorithm complexity. And again, I say, this is lots of the stuff we do runs normally in perfectly well in the average case, but that is unacceptable. Most of it, so when you look at Chomsky big O notation, we look at the complexity of algorithms. That big O is talking about the average time complexity. And most algorithms, most library functions, most of the sort of the research in algorithmic and data complexity considers the average case, is optimized for the average case. And that's marvelous unless you're operating on a real-time audio thread, in which case it's disastrous. You have to consider the worst case, because jitter is the bane of audio performance. So glitches, it's not necessarily always writing inefficient code. You could just be doing the work on the wrong thread, as we said before. My main thing, my clincher for this is, as soon as you start writing any audio-related code, that audio render thread, at least in debug build, leave the audio render thread instrumented. So measure how long you take. Measure each of the, if you've got multiple steps in your pipeline, measure how long they take. Keep an eye on that. That's your goal thing. Count the number of underruns. Maybe you didn't hear an underrun, because on your system it didn't manifest, but that same underrun would destroy someone's speakers. So leave your instrumentation in all the time and treat any kind of underrun as like the most important thing, apart from all the other bugs. And tied with this is the data structure complexity. And so the poster child for this is stood vector. Now, often we choose different data types in C++ for different reasons, but common wisdom is if you're going to choose a data type, use a vector. Why do we use a vector? It's simple, but most of the cunning things, like if you use a stood map for something very complicated, and it's cool, but most of the stuff we do, you just want to iterate through data, and a vector that's contiguous data in memory, you get cache effects that just speed you along. Vector is wonderful. And you should use vectors everywhere on the audio thread if you can, except don't ever write or don't ever append data to a vector on the audio thread. Why? Well, it's normally absolutely fine. Append another item onto the vector, put something on the end. Apart from that one case in a million where the vector needs to reallocate itself, the memory underneath, you hit a memory allocation, and then every now and again, and you can't trace it, you can't find out why, your system stalls because the vector is reallocating its memory. So the vector is a beautiful data structure that's optimized for the average case, and it works beautifully for the average case, reading and writing on an audio thread or any other system. But if you have a hard real-time constraint, never, ever, ever write to a vector, append data to a vector, ever. Remove anything from a vector, ever. Just don't do it. So anything that runs in unbounded time. What runs in unbounded time? The classic is locks. And we know why we shouldn't be taking any locks on the audio thread, yeah? Deadlock, meh, that's not the reason, because if you deadlock, then it doesn't matter. It's not a dropout. That's a disastrous audio. That's a disastrous programming problem. You may as well just give up and become a nun. But priority inversion, that's the kicker. So if you take any lock on the audio thread, and the UI or some other thread is already holding that lock, your audio thread is wedged until the UI finishes printing a spinning teapot on the screen. Disaster. So we should never take any locks. This is it's just the rules. Some people sort of take a more relaxed approach. Locks are fine as long as you use them responsibly and you know what you're doing. As long as you're only locking around something that's very unlikely to have any contention on it, or so we know whoever's going to have the other claimant of the lock is only going to do something very quickly within microseconds, then release the lock. It will all be fine. Good luck. Probably fine, but this is the thing, it's probably fine. And I have seen that code, and then somebody else added an extra thing, went, oh, that's a locked, that's a mutex block, so I'll just add some extra stuff in here. And then suddenly, without you realizing it, 2 years later, that mutex section is huge and causing you dropouts everywhere. So be relaxed if you like, but just, you know, deal with it. So, how do we break the no locks rule? Easy. Don't use locks. Okay, so in the real world, how do we not use locks? There are plenty of very good lock-free, wait-free data structures. I will not present you any, but they are there. Use them. Some of the standard received wisdom of communicating from the audio thread to the UI thread, some of the things your libraries will give you may not actually be as lock-free as you expect. I have been surprised by some of those primitives that told me this is how to communicate back to the UI thread that took a lock. Most of the time it works, but in some environments, like I had this communication mechanism cause me problems when running as an RTAS plugin on Win32 only. There was some pathological special case about that piece of library code that meant that it just massively stalled when trying to send data back to the UI thread. So use things you definitely trust and be very careful about who you trust. Sometimes your friends are not very friendly. So for those kind of streaming things, use lock-free, wait-free data structures and use atomic data. That's two things, and we'll look at these a bit later on. Be very careful about your data model. Use things that are known not to tear on your platform, if you know what your platform is now and what it might be in the future, or use atomic wrappers around data types. These things exist in our languages these days, and we're grown up boys and girls, and we can use them. Use them. I was just talking about stood vector reallocating. The golden rule, no memory allocation. This is the one. This whole talk is basically a series of whinges about all the things I have seen go wrong on many audio projects that I have worked on. And this is the classic. Most people know not to use locks. That's kind of obvious. No memory allocation, it seems to be something that everyone agrees with and aspires to, but everyone's just allocating memory willy-nilly on the audio thread, either because they know it or because they don't realize, again, what the things they do under the cover. So never allocate any memory on the audio thread ever. Just know, and don't call anything else that might allocate memory. Why should we not allocate any memory? Because most platforms' memory allocators take locks. That's reason number one. Reason number two, most platforms' memory allocators do not run in fixed size. The rule here is don't perform operations if you don't know exactly how long they take. Some of the memory allocators they're almost always optimized for the average case, which is great for the average person. But when it has to deal with some fragmentation or work out how to readjust its tables, it may run in unbounded time and it may cause you to stall. So the rule is no memory allocation, and be very careful about what you call, because many other things you call, unbeknownst to you, even in well-regarded libraries or frameworks, allocate behind your back and you don't know about it. How do we break the no memory allocation rule? It isn't actually that hard, but you have to do it intentionally. Use custom allocators for your audio thread. Isn't that just memory allocation? Yes, but it's memory allocation you trust because you're intentionally using it. You're reducing contention, one, but also you know the behavioral characteristics. So boost memory pool is great, for example. So you can make a custom allocator around a boost memory pool, and it's very simple. And the Dudley malloc, I've seen some code bases basically take that. That's the thing that's used as the standard on, I think, many BSDs, and sort of have their own copy of that. But again, that still is optimized for the average case, but if you reduce contention, you probably get away with it. But your own custom allocator for the audio thread, that is the right answer. Or, far more simply, just pre-allocate all the flipping memory you need up front. Just like go for the worst case, as long as your platform allows you to do this, and then you do not need to allocate any memory dynamically. Win! Simplifies the code and removes all the allocations. That's kind of like an ideal. Otherwise, the winning solution is do all your memory allocation for these kind of things on the UI thread and pass the memory safely down to the audio thread. So you just have... These solutions are all really important because they basically baked into the design. This stuff isn't something you can easily cram in later. And most of the rules that we're talking about here that we need to break, you have to sort of build into the DNA of your audio app early. You can't sort of retrofit a good threading model or remove all the audio, all the memory allocation on the audio thread by the time you've got 6 million lines of code. So this is fundamental stuff that we have to get right from the beginning. If you haven't done it right yet, and you're 4 years into a project, you're doomed. The next rule, no logging on the audio thread. So many audio apps with all the diagnostics for how things are doing on the audio thread, and if you do an NS log or a printf, you're doomed. Why? Because those things lock. Disaster. And then, oh, I've got some glitches, so I'll print out the diagnostics of the audio thread performance. Like, it's even worse than it was before. Oh, so I'll put some more logging around the printf to find out. So, oh my word, sort it out. How do you break that rule? Easy. Use a better logging library. And again, you have to use one that you trust. And maybe that's the one you write yourself. Just put the data in a circular buffer, read it back out, do the printf on another audio thread. It's not hard, but just don't pepper your audio thread with debug statements. Terrible. So, this, as I say, this is me taking away all of your shiny toys. The next step up, no operating system calls whatsoever, because they could lock. Most operating systems have various things will just be taking locks for certain functionality. The only time you could break this if you're using an actual real-time operating system that guarantees you the performance of the system calls. I'm pretty certain that apart from some classes of embedded products, most of us aren't using those kind of operating systems, so no OS calls whatsoever on your audio thread. Basically, all you can do on your audio thread is, shuffle some numbers and be done with it. It's just boring, isn't it? No disk access. This was a bugbear of mine. I've looked at a number of different streaming engines in different audio products, and my word, when I looked at them, and on the audio thread, there is a call to fread. It's like, that's not a streaming audio engine. That's a disaster just waiting to happen. For obvious reasons, you cannot perform any file I/O networked or attached storage on the audio thread because you just don't know seek times. The seek time, even if it was a performant read, is probably longer than your audio buffer period. It's just out of the question. And again, because the operating system's allowing multiple threads to access the file system, it's probably taking a lock. No disk access. And again, we fixed this by pulling all disk access onto another thread and carefully managing audio buffers between that file read thread and the audio thread. These are things that we must do. If you don't do that, it's not a disk streaming engine, it's a disaster. Similarly, no network activity on the audio thread. Now, the Waves guys were talking about the SoundGrid thing yesterday, a beautiful networked system. I'm sure that they know what they're doing and they don't do any network activity on the audio thread. We just have no idea. So basically, OS calls literally do nothing on the audio thread that you do not trust. This even includes any other third-party libraries. I've already voiced my distrust of major frameworks in various libraries. Anything you call could allocate memory, could make an OS call, could call some other third-party code, may wait till you go out, call all its friends round, have a party, drink all your booze, destroy it when your parents come home. It'll be a disaster. Don't trust anyone, even if you think they're your friends, unless you inspect or the thing comes with a real-time guarantee. And now, I'm not going to name names, but some very well-known bits of platform that say, we are thread safe and we are performant. I pretty much guarantee you they are performant because they were not thread safe. So, I didn't lock, but I fell apart. So even if they tell you something, you have to inspect and measure and measure and measure. Trust no one. What a sad world we live in. Love all, trust a few, do wrong to none. That's basically the motto we have to work with. Even stepping further back, our choices of language, there's given up on the arguments about what language is better for certain things. Most of us are coding this DSP stuff in a C-like language, that's fine. But again, it's pretty obvious, but there's nothing wrong with interpreted code per se if you know it's guaranteed to run within the CPU budget, but most interpreters come with a baggage of garbage collection or whatever, or ref counting, and so you have to be very careful what you're doing. That's probably not an issue for us because we're probably mostly coding in these languages. But if your code, maybe you're all mostly C++ devs. Obviously, we are grown-ups and we use RAII, resource acquisition, initialization, smart pointers, and all that kind of stuff. This is great. But again, those are pernicious little beasties. If you're using something in a shared pointer on the audio thread, and on the audio thread, you let go of the last shared pointer to it, then you may be deallocating that thing on the audio thread, and you don't notice it. So that's kind of like a big super hint, and the cause of a number of bugs that I've seen in the past, latency bugs, is treat your smart pointers on the audio thread with super care, and actually have a wrapped smart pointer that when the last one goes away, moves the work onto another queue to be flushed on the audio thread or something. Use a cleverer smart pointer, a smarter smart pointer. So for this rule, basically it's a sad world we live in. The constraints of your system may vary, but the rules are assume the worst, any operating system, any library call, anything you do may block. Tying your shoelaces may block. Use RAI with caveats. Specifically use your own memory pools and good message queues. And there's this interesting dichotomy, because often when we're doing this kind of work, I would say in other contexts, don't roll your own. Don't, the not invented here policy is often dangerous, and if you write your own thing rather than taking something off the shelf, then you're likely to introduce your own bugs, and you haven't had the experience of making a lock-free queue or something where some expert has. So ordinarily, I'd say always use some third-party code that's trusted, that's peer-reviewed, that's been in use for years. However, if you write it yourself, you trust it, and again, all bugs are your own. So I like my own bugs. I don't like other people's bugs. That's our main. That is the golden rule of audio programming, really. So how are we doing for time? Ooh. I'm having fun, I don't know if you are. Respect threads, rule number 3. So, of course, this quote has nothing to do with actual threads, but again, Victor Hugo's cool. Surprising thing number 1, don't presume the audio thread is the audio thread. This is, so I wrote some beautiful lock-free data structures making the presumption that the audio thread runs over here and it's high priority, the UI thread runs over here and there's only one producer, one consumer, and it's not too hard to write a reasonable, careful lock-free data structure. And then logic comes along and pumps you for audio on the UI thread, and it completely destroys the world. So don't always presume that the audio thread is actually the real-time high-priority thread, because you'll get run in some context where that presumption doesn't hold. But mostly when we think about, well, there are a few things we think about threading, not just this whole don't lock bobbins. Data tearing is the classic respecting threads issue. When we try to push, say, the calculating coefficients of a biquad, say, which may be slow, if we push the calculating of the coefficients off the audio thread and we just run the biquad on the audio thread, genius. So how are we going to do that? We have a structure for those coefficients, and then down here on the UI thread, obvs, then we calculate the coefficients, and then the audio thread can run with those coefficients. That's efficient code now, because we're not going to do all this shenanigans on the audio thread, which could run in goodness knows how long. Genius. Except, what is the problem? Tearing. So we're halfway through updating these, and then the audio thread kicks in, runs your biquad in random state, and then you finish off with the things, and so you end up with some kind of unstable audio filter or pops and clicks, and it sounds disastrous. We don't want to do that. So obviously, we know how to fix that, yeah? Mutexes! No. So you just have to think about this stuff. It's not too hard to have solutions to that. Rather than just updating the coefficients in place, have 2 sets of coefficients, and the audio thread works with a pointer to the current one, update another set of coefficients in the background, and then basically just switch it atomically on the audio thread. Now we're coming to the sort of one of those things about threading we have to think about. Understand what data types are tear-free and what tear. On most major platforms, int, bool, which is probably an int, float, and pointers are all atomic. So if you do this very carefully, because there are other issues rather than just, oh, this particular value doesn't tear. But you can do this, and that right would be safe. So update your data to the side and switch just an atomic data type. That's not cheating, it's just the right way of doing it. Using your brains carefully, because long and double, depending on your platform may or may not be tear-free. If your long is 64-bit, but you're on a 32-bit platform, then that probably tears because the CPU is going to write the first 32 bits. You could swap before it writes the second 32 bits to memory. So just use your brain. But these guys are tear-free, so respect that. The data model of your code, though, that was an example of some of the data model. Think about where your data lives. Does it live on the UI thread or does it live on the audio thread? The right answer is all of your data, if you're playing back or storing step sequence data, it lives on the UI thread and you have a renderable copy on the audio thread. If your audio thread tries to edit that sort of the data, you're going to end up in terrible sticky problems and you're going to end up mutexing stuff. Don't do that. Your data lives, the whole design, the fundamental design of your data model should be the data lives on the UI thread. Depending on what you do, the main issues there may be if you're having automation sort of driven in real time on the audio thread, how are you going to have that change to the data model that is actioned on the audio thread, on the UI thread? Those are problems you have to solve and solve well at the beginning because you're going to struggle to get them in later on. So that's what we've covered that ground already. Choosing the right data representation then is, I guess, the final golden rule we should look at. In God we trust, all others must bring data. Just talking data representation. Most of us are probably writing audio, processing things using float because that's just the easiest thing. It's what the frameworks give us. It's the presumption. Oh, floats are good. If you're doing any audio processing and you don't know how floats work, stop, learn how floats work, and then do your audio processing. Understanding the difference between your calculations in the floating point, i.e. EE754 representation, or fixed point audio. Fixed point audio manipulation is terrible, awful, looks ugly, requires you to use your brain. It's great because it requires you to use your brain. It requires you to be very explicit about underflow and overflow and basically you could introduce errors with your bad fixed point arithmetic, but you could avoid an awful lot of terrible problems that you can back yourself into with float. So I am not advocating just, if your entire audio path right now is floating point, stop, go and rewrite it in fixed point. I am advocating you understand the difference between the two ways of shoveling audio, the fundamental differences between them. And there is no better floating point sort of number representation than what is built into the IEEE754. It's beautiful, it's clever, it's ingenious, it's very good, and it has surprising problems. Surprising problems when you get down to infinitesimal size or very large size. You lose precision, but your code those surprising things are not evident in the code. Whereas in fixed point, you see very clearly where your resolution falls over, or where you hit overflow or underflow. And with fixed point, you don't run into some of those terrible problems like random not numbers, the denormals, those subnormal numbers as you approach zero. There are tricks with floating point numbers to avoid denormals, like feeding in sort of low-level noise in order to avoid subnormal stuff. We can't go into that in any kind of detail, but if you don't know about fixed point audio processing, and I know lots of people don't, learn about it, actually work out, go through some examples, do some fixed point stuff. It's interesting, it forces you to think about all these kind of problems that you may encounter. If nothing else, will inform what you're doing in the floating point domain. The choice you make is, as I say, is often you're already in float or your platform takes you one way or the other. That's fine. If you want to go to double, you can't just go to double and that solves your problem. It brings in different sets of problems. It just means the resolution limit falls off somewhere else, and you could end up with some strange tearing if you're in a 32-bit world for 64-bit floating point numbers. You could potentially break the rule by pulling in a C++ fixed point library that just does it all for you. Often that's the bad idea, because what you can do with the fixed point maths is do a number of operations and then sort of bring your, sort of renormalize your fixed point number down later on in the chain. And if you're using a fixed point library, often it will just sort of renormalize every single operation, and so it won't be as efficient as hand-rolling your fixed point audio code yourself. So just be aware of it. It's very important. So these are the 4 golden rules, I think. Keep within your CPU budget. And the corollary, if you don't know how long it will take, don't do it, which is basically do so little stuff on the audio thread, it hurts. Respect threads and choose the right data representation. So, since I need quotes to prove that everything I'm saying is correct, here are some more quotes. The rules of survival never change, whether in a desert or an arena. Bear Grylls, another awesome audio programmer. Leon Trotsky, you know, again, a well-known, respected audio geek. There are no absolute rules of conduct other than peace or war. Everything depends on circumstances. So everything I say depends on circumstances. Every decision you make is in the context of your particular problem on your particular platform. So maybe you can say, oh, my process is fast enough so I don't have to spend time here. I can expect my multi-threaded system to cover this. That's fine. But only do that with your brain switched on. Don't just rely on CPUs to be fast enough. Debussy, works of art make no rules. We were building works of art, yeah? Rules do not make works of art, so ignore the rules. And the most important quote of all, Mr. T, I believe in the golden rule. Remember the gold, rules. So, that's it. Thank you very much for listening.